Hello dear students, we will continue our discussion on understanding the particle motion in a variety of electric and magnetic fields. So far we have studied the motion of charged particle in the presence of static uniform electric field and magnetic field. So in today's class, we will try to understand how will the particle move in the presence of a perpendicular static uniform electric and magnetic field. Perpendicular, static and uniform electric field and magnetic field. So, these two fields are perpendicular to each other. So, let us say we consider the coordinate system like this. Like this, and let us say this is x, y, z. Take the electric field to be in this direction and the magnetic field to be in this direction. Now, the response of charged particle to a perpendicular component of electric field in the presence of the magnetic field. That is the basic outline of the topic. So, the particle's velocity and electric field being parallel to each other and at times being perpendicular to the velocity will make how the particle will behave. So, the perpendicular component of electric field will exert a force in the direction of magnetic field. So, if the particle is having some velocity, the perpendicular component of the electric field will exert a force in the direction of magnetic field, because these two fields are perpendicular to each other. So, then what happens? Electron will move freely in the direction opposite to the electric field. So, by nature, and ion will move freely in the direction of the electric field, right. So, the charged particles are now separated because of the electric field. So, they will produce an electric field which will try to cancel the original electric field, because the direction of the electric field thus produced by the charge separation will be opposite to the original electric field, right. So, as a result, no electric field, no resultant electric field will exist, and as a result no further forces will act along the electric field. So, let us say we consider the motion of particle in perpendicular electric and magnetic field configuration. The equation where we start our discussion will again be the same equation, F is equals to Q times E plus V cross B, the Lorentz force. So, let us assume for this discussion, let us assume the magnetic field along the z axis and the electric field to be in the along the y axis. We will try to understand how the motion will be different in with respect to the uniform magnetic field, right. Let us say we have a particle which has no initial velocity along the y direction. What have we assumed? We have assumed the electric field to be along E and magnetic field to be along the z axis. Now, since the particle has no initial velocity along the y direction, there will not be any force because of the magnetic field. Why? Because the velocity of the particle is 0. Because you see this magnetic field can only act in the presence of a non-zero velocity. So, velocity is 0. That is why there will not be any force. But the moment electric field is there, electric field will cause the particle to move along the y direction, and the particle will gain some velocity. Now, the magnetic force will start to act on the particle, because the particle has now a non-zero velocity. Magnetic field will have its effect and deflect the particle sideways. That means, it will try to move the particle in a circular path, right. The moment it has some velocity, it will try to, now we are talking about the y directional velocity. So, obviously, the z and x directional velocities will constitute the circular motion, will be responsible for the circular motion. So, velocity, the particle, the magnetic field will try to move the particle in the side direction. So, the velocity of the particle will now vary and will come back to 0, okay, because of the effect of the magnetic field. It will not allow the particle to accelerate in a linear way along the y direction, Because of this, the particle's velocity will again come to 0. But the electric field will again start influencing the particle, and under the influence, the whole process is again repeated. So, this trajectory of the particle becomes what is called as a cycloid. Okay. So, particles with an initial velocity, the only difference if we have a particle which has some initial velocity to begin with, is that the trajectory of the particle will not be a cycloid, rather it will be a torchoid. Okay. Since the particle already has a velocity along y direction under the influence of magnetic field, the particle will of course gyrate, and the gyro radius is in the positive y axis get enhanced, and the velocity does not change to 0 as it touches the x axis. Right. So, particle will move something like this. Now, let us try to derive some equations which will represent this movement. Now, let us construct the coordinate system. Let us say we now start with, we say x, y, z. We take the electric field to be in this plane E, which is in the xz plane, and the magnetic field is along the z direction. So, this becomes Bz. B, of course, is along the z direction. So, I have kept Bz. So, the electric field is in the xz plane, and the magnetic field is along the z direction. Right. Now, where do we start? We start with F is m d square x by dt square is equals to q times E plus V cross B. Now, ideally, I can take the position to be r rather than x, dealing with the 3-dimensional coordinates. Right. Now, one thing is simple. We have dealt with parts of this right hand side individually. For example, when we were discussing the isolated static uniform electric field, we considered F is equals to EQ, and Vz was, or V along the direction is simply E by m t, right. That means we have dealt with the uniform electric field separately, and we also dealt with the second part, which is the uniform static magnetic field separately. Let us say we have studied this first, and then we have studied this part. Now, can I be wrong if I say that the resultant motion of a particle in a situation where we have electric and magnetic fields, both of them, will be a combined motion of 1 and 2. Right. So, if I take it, let us say, if I recall both the sets of equations, we will write m dvx by dt is 0, m dvy by dt is again 0, and m dvz by dt is q ez. Okay. Now, similarly, when we have only the magnetic field, we can write m dvx by dt is q vy bz, m dvy by dt is minus q vx bz, and m dvz by dt will be 0. Right. Now, you have to understand the magnetic field is along the z axis according to these set of equations, and according to these set of equations, the electric field is also along the z axis. Right. Now, we have equations for isolated electric field, isolated magnetic field. Now, let us combine both of them for a perpendicular E and B field configuration. So, the z component of the velocity will not be influenced by the magnetic field, as it is parallel to the as it is parallel to the magnetic field. So, we can say that these two equations combined will remain the same, right, because dVz by dt is 0 according to the first equation. So, we will write q Ez. Let us say we call this equation as 1, this as Roman 1 and this as 2. What are we doing? We are trying to combine the both the sets of equations for understanding the motion of particle. Right. What does equation number 2 suggest? So, if you integrate this equation, we will get something like this. Vz is q Ez by m, of course, m is there. Since we are integrating, you will get time on the right hand side plus a constant which you are going to obviously call as the initial velocity. Right. So, what does it suggest? It suggests that there will be linear acceleration along the z axis or the z component of the electric field. So, you have the electric field in the x z plane. So, you can obviously resolve this electric field along z axis or along x axis, that is fine. But the point is, you will have the velocity Vz only influenced by the electric field. So, which is q by m E z t plus Vz0. Right. Now, let us look at the other components of velocity. Let us say we consider the x component of velocity. Okay. Now, since the electric field E can be resolved to have components along x as well as z direction. So, we have taken care of z direction of the electric field and this is what we have got. The z direction of the electric field will accelerate the particle along the z direction, but it will be uninfluenced by the magnetic field which is along the same direction, right. This is what it is. So, this is the constant velocity. But when you look at the x direction of the electric field, you resolve this E to have a component Ex. Okay. This is just a component, this is a scalar component. Okay. If you have an Ex, then what will happen is this Ex will of course accelerate the particle along the x direction, but the velocity will also be affected by the magnetic field. So, if you want to combine these two things, let us say, if you want to combine these two things, this will no longer be just 0. You are trying to project this geometry of electric and magnetic field onto this equation. So, this will be q times Ex, right. So, now the equations cannot be just combined just like that. So, we will write m dVx by dt will be q by m, no, it is q Ex, right, q Ex plus minus q by m Vy b. That is what we have here, right, dVx by dt, q by m Vy Bz and q Ex, sorry, q by m Ex. Now, if I have written q by m for the magnetic field part, I should remove it here and I should write it like this. Now, the plus minus, what is the purpose of this plus minus? See, one thing is sure, the magnetic field will only be able to turn the particle in a particular direction and this direction depends on the charge of the particle. So, as to account this, I will keep plus minus so that positive charges will be in the positive direction and negative charges will be exactly in the opposite direction. So, what is the purpose of plus minus? It is facilitating the direction of the circular motion, right. What else is there about it? So, similarly, we can have the third equation. What is it? You see, Vx we have taken care of, Vz we have taken care of, Vy. Is there any component of electric field along the y direction? No, it is not there. So, Ey is of course, let us say we write it as equation number 3 and 4. Ey is 0. So, obviously, m dvy by dt is 0 for the electric field, and m dvy by dt is q minus q vx bz, right. So, we have to combine these two things, isn't it? So, we will write dvy by dt is minus q by m vx bz, or more conveniently we want to still have that plus minus factor, right. So, this will become minus plus because there is already a minus, and qb by m is omega c v x d vy by dt. This is one equation. So, this is equation number 5. So, the equations which are representative of the charged particles movement are, what are those equations? This one, and then this one, and this one, right. So, can we write them together so that we can easily understand? So, the equations which represent the particles motion in the perpendicular E and B field configuration are these. So, it will be m d vz by dt is q ez, m dvx by dt is q ex plus minus q ex q bz vy, and m dvy by dt is minus plus q bz vx, right. Let us say we call this as Roman 1. So, we take double derivatives of these equations. Say t square v x by dt square. This square v x by dt square will be, you have to, charge is a constant, the electric field can be assumed to be a constant. You have to do it by assuming E x to be constant in time. That means static electric field. So, this will be 0, right, this will be 0, and plus minus m is there, q bz by m dvy by dt, right. So, d square vx by dt square is plus minus omega c. Omega c is the angular frequency, qb by m is omega c, right. Omega c times dvy by dt. Now, we will use dvy by dt here. From this equation, we will substitute on the right hand side. Then we will write d square vx by dt square is plus minus omega c, dvy by dt is minus plus q bz by m times vx, right. So, this is multiplication here within the bracket. So, d square vx by dt square minus plus multiplying plus minus will result in a minus, and qb by m being omega c square, because qb by m is omega c multiplied by omega c is omega c square times Vx. Now we have a very interesting equation. D square Vx by dt square is minus omega c square Vx. Right. Let us see the other equation. What have we done so far? We have taken a derivative of, let's say this is A, B, C. Time derivative of Roman 1 B, right. Let us take time derivative of Roman 1 C, will be m d square Vy by dt square is equals to minus plus q bz d Vx by dt. Right, this is what we have. So we have to now substitute dVx by dt from Roman 1b. Okay, we will do that. M d square Vy by dt square is equals to minus plus, or rather what I'll do is I'll take this mass onto the other side and I write q Pz by m, just one step for the sake of clarity, right. So we'll write t square Vy by dt square, qb by m is omega c, right. So minus plus omega c dVx by dt. So we'll bring dVx by dt from the equation 1b. This is qex plus qbz Vy, qex plus qbz Vy. If I correct, there will be a mass in the denominator, right, qb. Now we have something interesting. So this will be simplified as minus plus q by m omega c ex plus minus omega c square Vy. Why, you ask? qb by m is omega c. Omega c is plus minus qb by m. qb by m is plus minus omega c. Taken the same correspondence. Omega c is already there here, so it will multiply and will have omega c square. And d square Vy by dt square is, taking this minus plus inside, I will be able to write q by m. Omega c is qb by m, right. Q by m is omega c by b. That means I have to write omega c square by bz ex. You have a minus here, right. You have a plus minus here. Multiplying minus plus will give you minus. These two things again, minus omega c square Vy. So don't be confused with the algebra. I'll just tell you what I have done so far. I have substituted for Vx by dVx by dt into this. I have taken this omega c inside. You see here there is an omega c already existing, which gave you omega c square, and here omega c is not there, but q by m is there. So q by m can be written as omega c by b from this, which gives you omega c square by b, and Ex is still there. About the plus minus and minus plus, qb by m, so we write omega c is plus minus qb by m. The role of this plus minus is to indicate the direction of the circular motion, right. So I have used plus minus where it is not there. Let's say QB by M I have replaced for omega c. So, this plus minus has to be brought along. So, that is what I have done, and this is a minus plus which is available right outside. So, here Q by M omega c when converted to omega c will give you a plus minus. Minus plus multiplied by plus minus will give you a minus. Again minus plus multiplied by plus minus will give you a minus. So, we can summarize this equation as d square Vy by dt square as minus omega c square times Ex by Bz plus Vy. You look at this equation needs a lot of understanding. It says the rate of change of velocity, okay, d square, the second rate, the d square Vy by dt square has some angular frequency component, but in addition it has this information about the electric field also. What it means, for you to understand that, we have to go back to the preliminary equations. So, along the x direction, see along the z direction it is only electric field which is acting, and along the y direction it is only the magnetic field which is acting. But along the z direction you have the net acceleration dependent on the magnitude of electric field and the magnetic field. So, that is why in your equation on the right hand side you have both. So, you see this factor Ex by B. So, you know Ex by B is in the units of velocity, right? We know that. So, the velocity Vy is being added by an additional velocity which seems to be a function of the electric field and the magnetic field. Okay. So, we will stop it here today. In the next lecture, we will write this equation in a slightly modified form, and ultimately we have to seek solution. Until and unless we know what exactly is Vx, what exactly is Vy, what exactly is Vz, we will not be able to tell any inference about the particle's motion. So, that we will do it in the next lecture.